Okay, in this video we are going to cover the mixtures model. This model tries to explain how a substance dissolved in a fluid behaves through the time. To do so, we have to define some concepts. For example, the first concept is the mixture. The mixture is usually a material dissolved in water. For example, let me give you one example. Salt dissolved in water. All right, how many grams of salt is dissolved in water? Another example is sugar. Sugar dissolved in water. How sweet or not sweet the water it is. So that is the mixture of a material with the water. Okay, how sweet or how salty solution is measured in terms of concentration. Concentration is the measure of how many grams of salt or grams of sugar is dissolved per liter. So that is the definition of concentration. Now, this is in the metric system, but you can also define that in the English unit. Sorry, and it will be like how many pounds of salt or sugar or whatever is dissolved per gallon. All right. So that is the definition of concentration. How many of the material is dissolved per liter or per gallon? Okay, now another thing we are going to define here is the fluid flow rate, the speed of the fluid coming in or out. Okay, the flow rate is measured in liters per minute. It could be liters per second or liters per hour, but in the end it's just the volume divided by the time. Here the liters per minute is in metric system, and here gallons per minute is in the English system. Now, the combination of these two actually produces a linear differential equation. Okay, so assume that you have a tank with a fluid, with could be usually is water, okay, but here you have a mixture of salt dissolved in this tank, okay. Now, let's define two concepts: the concentration input and the flow rate input, and the concentration output, flow rate output. Now, as I said before, the concentration input is the grams per liter or grams per volume, and the flow rate is the volume per the time. Okay. Here we have an output because we have a concentration output and we have a flow rate output. Okay. Now this tank is going to be very well mixed, so the solution or the quantity of material dissolved in the water is constant. It is homogeneous. All right. Now let me give you one important concept. What happens if the flow rate is equal to the flow rate output? The input and the output flow rates are the same. Okay. Here I am. What happens if the flow rates are the same? Well, the quantity of liquid coming in and coming out, they are the same, then the volume is going to remain constant, right? But that is not always the truth. What happens if the flow rate is bigger than the flow rate output? The input is bigger than the flow rate output. So then the volume is not going to be constant, it's going to increase. Now, what happens if the flow rate here, and I have a mistake here, oh no, sorry, it's okay. What happens if the flow rate output is bigger than the flow rate input? So what happens here is that the volume is going to decrease. So the volume in the tank could be constant or could be variable. Okay, just keep in mind that that concept. Okay, now let me tell you what is Q of T. Q of T is actually the quantity of salt dissolved in the tank. So here is how many grams of salt is dissolved here, or how many grams of sugar is dissolved here. So that is the quantity. So the Q of T is measured either in grams or in pounds. But that is the quantity of the material, all right? Okay, now, what happens if we do the multiplication of the concentration input times the flow rate input? Well, actually, it doesn't matter. What happens if we do the multiplication of concentration times flow rate? So in terms of the units, here the units is going to be grams in metric units per liter. So that is the concentration. And then if we multiply times the flow rate, it's going to be liter over the minute, over the time. So you can see here the liters cancels, alright? Now what happens if you do it in the English units? Okay, in the English units, it's going to be the same because this times this, the gallons are going to cancel and you will get pounds per minute. Okay, because the quantity of salt dissolved is measured in grams or pounds. Okay, so what happens here is the resulting units here is grams per minute, meaning the Q of T divided by the time. And this is because this comes from flow rate, and flow rate is speed. Then this multiplication leads to the derivative of Q of T respect to the time. So the derivative of Q of T respect to the time, the units of this will be grams per minute if the time is measured in minutes. Okay, but it's not going to be equal, okay? Because what happens if the concentration input is equal to the concentration output? Then the quantity of salt dissolved here is going to remain constant, so it doesn't change anything. Okay, so the model goes like this. What it should happen is that here we should have a difference, and here in compared to the output. If the input and the output they are the same, then nothing changes here. At least one of them should change. Okay, so here the derivative of the quantity respect to the time is going to be equal to the rate input minus rate output. What is the rate input? The rate input is here is going to be the concentration input times flow rate input minus the concentration output, flow rate output. So that is the derivative of the Q of T respect to the time. Now remember that we are trying to measure how the quantity of salt or sugar is dissolved in the tank. Okay, but here we have the rate, so we have the derivative. Okay, so this is actually the differential equation. This is the differential equation. What the problem should give you is the concentration input, concentration output, and the flow rate output. But one thing you have to calculate is the concentration output, because the concentration output is going to come from the what is the quantity of salt here in the tank divided by the volume, and the volume could be variable. It could be constant, but could be variable. So let me change the differential equation. So the differential equation is going to be the differential of derivative of Qt respect to the time equal to the concentration input, flow rate input minus the concentration output. The concentration output is going to be the Q of T divided by the volume. Volume as a function of time, because it could be variable, times the flow rate output. Okay, so what happens here is, if you pass this to the other side, is that you are going to get this differential equation. The derivative of the Q of T respect to the time plus this to the other side is going to be volume flow rate output divided by the volume as a function of the time times Q of T is equal to concentration input, flow rate input. Okay, now what happens here is that this is a linear differential equation, okay, where this is P of T and this is Q of T. All right, well, different Q. Okay, now, so that is a linear differential equation. So one thing very difficult to calculate maybe is the volume as a function of time, but we will see that with an example in the next video. Some students in previous semester asked me, where is the proportionality? Why this one doesn't have a proportionality K, just like in the population model or the warming cooling Newton's model? Well, there is no proportionality here because the concentration is equal. So you don't have like environment properties, or the environment doesn't change how the concentration is measured. So that is why it's exactly equal. So there is no proportionality. It's just the concentration that is here and the concentration that is here. The delta of that concentration affects here the rate of the concentration in the tank. Okay, applications of these are in the painting when they try to make a, let's say like a brown color. So they have to introduce some color with some flow rate and some concentration in order to mix the in that case the bucket to get the color that they want, because the color is going to have certain quantity of that color dissolved in the white paint. But that is one application. The other application is the water treatment plants, where you have coming here dirty water and you want to clean it. So that means that you want the dirty to go away. So you want the QFT to go to zero in large tanks. Okay, so on the next video we are going to see an example of how to solve these kind of problems using this differential equation. Okay, so just keep in mind this part of the differential equation. And again, what the problem should give you is the concentration input, flow rate input, and the flow rate output. The rest you have to calculate it. All right, see you on the next video.